Hello and welcome back. This time we've got another fun circuit board project related to my work on the Porsche 914, formalizing the fuel gauge driver. I'll be designing the schematic, getting the board made, trying to solder on microscopic parts, and updating the firmware that makes it all work. This will be my most ambitious circuit board project, well, since about 1982, but that's a story for another time. Please feed the YouTube algorithm by giving the video a like. If you want to see more like this, click subscribe and ring the bell to be notified of new videos. If you want to chip in on my expenses, I now have Patreon and YouTube memberships. This project and the short video series to follow is a follow-up to my Porsche 914 upgrade project video number 31, Hacking the Fuel Gauge. Back in February, I soldered up an ESP32 microcontroller-based breadboard to drive the car's analog fuel gauge pointer to reflect the state of charge of my battery pack, and also light up the low fuel light when the charge gets to a low level. It works well, but my long-term goal is to make a real circuit board for it, while also expanding the functionality to make it useful to others in the EV conversion world who have a wide variety of target vehicles and components. So after you watch the video, let me know if you think it would be good to do a small production run of this board. I could either sell them myself or maybe partner with EVTV as the distributor. Now let's define the requirements. Power the board with the car's 12-volt power supply, a USB-C cable, or a JTAG debugging cable. Read the pack voltage, either over Wi-Fi from an EVTV V2 controller or by a wired connection to the pack. Drive an analog fuel gauge representing the state of charge. Light up the low fuel light for a low state of charge. Use a CAN bus driver chip and firmware to monitor and inject packets into a CAN bus data stream. Provide a built-in set of web pages to assign values and perform calibrations without the need to change any hard-coded values in the firmware. And finally, open source the board design and the firmware. The first effort is to formalize the prototype and implement the rest of the necessary circuitry. I spent a few days drawing out the schematic in Fusion 360. I'll briefly show you each subsection as I walk you through. The ESP32 design is straightforward, with digital and analog ins and outs, a blinky LED, and I added a JTAG header for firmware updates and hardware debugging with Visual Studio, the Platform I/O plugin, and an ESP-Prog debugging board. I've done previous videos on how to write and debug ESP32 firmware with this toolset. The MOSFET-based fuel gauge state of charge pointer and low charge light driver circuit came right out of the prototype, which goes into a 2-position screw-down terminal block. For car power, I made a reverse polarity protected 12-volt input from the car on another terminal block. The board can also get 5-volt power from the USB-C connector. You'll later see that I chose a USB-C connector that stands straight up from the board and is solidly soldered in for connector integrity. The USB-C data lines drive a standard UART chip connected to the ESP32's serial port. This connector can be used for firmware updates, debug output messages, and powering the board during firmware development. It's wired so the board will automatically reboot when a new firmware version is uploaded. A CAN bus driver chip was added to allow the board to be used as a generalized CAN bus controller in your car. It has a bus termination resistor with jumpers, so you can wire the board in at either end or in the middle of the CAN bus cable. In my case, I'll be able to use it to measure motor current via a LEM current sensor and monitor the charging state from my Thunderstruck charger. Now you can download and enhance the firmware to talk with any CAN bus device in your car, and I'd be happy if you contributed that back to the project for all of us to benefit from. Then there's a standard 3.3 volt regulator that is jumpered to either pull power from the car's 12 volts or the USB-C's 5 volts. Now all of that is pretty straightforward, but trying to physically measure pack voltage is where it gets really tricky. My pack's peak voltage is about 144 volts DC. And if I hooked up that to a pin on the ESP32, all of the magic smoke would come pouring out. So we have to solve that problem. Also, I never want the high voltage pack wiring to electrically connect to the 12-volt wiring in the car or the circuitry on the rest of this board. Keeping the pack voltage fully isolated is key here. So I did what every good engineer does. I searched around and stole somebody's design. No, I really have no knowledge in the world of isolated DC voltage measuring circuits. So I found a web page with a very good description and circuit design from simplecircuits.com, and I'll leave the full link down in the doodly-doo. The Simple Circuits project reads high voltage DC into an Arduino, and that's exactly what I'm looking for. I just had to adjust it from a 5-volt supply to a 3.3-volt supply. The key pieces are a DC to DC isolated power supply, a DC voltage scaler, and an opto-isolator. And this gives me complete isolation of the high voltage DC from the rest of the circuitry. Plus, I'm able to segregate all of this into its own side of the circuit board for physical isolation too. After getting the base design done, I added a ton of test points so I can easily clip leads from my meter and oscilloscope to see what's going on, and added many LEDs on interesting data and power lines to get a quick glance of the activity on the board. One of my meta goals was to make it easy to manufacture. Now, I've used JLC PCB for my circuit boards for years, and they have a sister company called LCSC that sells electronic components to anybody who wants to buy them. JLC PCB recently added full circuit board assembly service, but they really want you to design your board with components that LCSC has in its catalog and has in stock. And that was my first challenge, searching the LCSC catalog to find parts exactly the same as what I needed. If they didn't have the exact one, I'd search for something functionally equivalent. Now, the final aspect is to also find a part that exists and has a representation that can be loaded into Fusion's electronics design module. Without having a model of the part, I can't add it to the schematic, I can't connect the pins, and I can't place it on the circuit board or visualize it in a 3D representation of the board. What I found is that the situation is a pretty nasty Venn diagram. This one is for us Canadians. That's pretty accurate for your amusement. On top of all of that, JLC PCB considers some parts basic and some extended, and you pay a lot extra for extended parts. So I tried to look for alternatives on the basic list, but in the end I'll just have to bite the bullet on the extra cost. Fusion comes with a large library of common parts, but I'm using some uncommon things here, and there are ways to get part designs into Fusion, and the first one I tried was Library Loader from SAMAC. Now, SAMAC creates CAD models of parts, providing the schematic representation, the circuit board footprint, and the 3D package. Well, most of the time they provide 1, 2, or sometimes even all 3 of these necessary pieces. I used Library Loader successfully with older board designs using DesignSpark, but I just couldn't get it to work with Fusion. Fusion's electronics module is basically a repackaged Eagle, but library management has changed. So after pulling out most of my hair, I stumbled upon Snap Magic from Snap EDA. Now, this will take your part from their catalog and pull it right into a library in Fusion. It's beautiful. Except, again, when it only supplies 1 or 2 of the needed features for the part. So you can see that selecting a part for its characteristics, finding it in LCSC's catalog and in stock, then finding it in Snap EDA with all 3 of the required features, well, let's just say I don't have much hair left. I did end up having to draw a handful of part 3D representations, but Fusion has a great wizard that will generate it for you. In the end, I persisted and came through with a long LCSC bill of materials and a fully designed and rendered circuit board. Well, except for a couple of parts that LCSC just doesn't stock and literally had no substitute. If I decide to have JLC PCB make the boards and do an assembly in the future, I'll have to order the remainder of the parts from other suppliers and add them by hand afterward. So let's look at how the board turned out. Along the bottom you can see the screw-down terminals for all the ins and outs. Along the left edge is the DC high-voltage pack circuit and its terminals, physically separated by a gap from the rest of the board. In the upper right is the ESP32 module with the JTAG connector below. To the left are the low-voltage parts of the DC pack sensing circuitry. Under that are the USB-C connector and the UART chip. Below that is the CAN bus driver chip and its terminals. To the right of that are the MOSFETs driving the fuel gauge and the low charge light and their terminals. And in the bottom right is the 12-volt terminal and the 3.3-volt regulator. Turning on the bottom layer of the board, you can see that I set it up as a ground plane, and I made a big gap between the high and low voltage sections. To speed up the layout, I used and then tweaked the auto router to put the minimum number of signal and power traces on the back, but there's no way around having a few. Auto routers would be an excellent target for the tidal wave of AI stuff coming in now. Even the best auto router, which comes from the highly used Eagle, is not great. The board has 4 mounting holes to match a project box I found, but I think I might just design and 3D print one that's exactly the size I need. One issue I ran into was that it pretty much filled up the maximum board size you're allowed to have with the free version of Fusion. I'd upgrade to the paid version for bigger boards and more layers, but the price is just too high. Finally, let's look at the sweet 3D representation of the board. Besides being sexy, this view really helps me to know that I don't have any physical space conflicts, where the wires are coming in and out, and the mounting holes are clear. Okay, so that wraps it up for this introduction to the new project. Because you're so awesome for watching to the end, I'll give you a sneak peek at the circuit boards that I just got back from JLC PCB. Everything looks good from a fabrication standpoint, but I'm really scared about soldering on some of those components by hand. Like the USB-C connector is just wow. Take care, and I'll see you soon as I build up the board in the next video. Before we wrap up, I'd like to thank my Patreons and YouTube members, Peter Bouvier, Puppy, and Craig, for their ongoing support. I see that a whopping 96% of my viewers are not subscribers, so please go ahead and click that subscribe button because it really helps out the YouTube algorithm. Thanks and take care, and I'll see you in the next video.